Hi everyone, we are back and we are going to do our problem set 6 solution videos. So, sees candidly, sells chocolate boxes, said to be random, normally distributed, with a mean of this, population of this, dedicated to the pursuit of statistical analysis, a sample, there's 710, so we sample 1,700 pieces at random, and we find, so the observed, so we find our number is going to be 950, observed, expected. So diameter greater than 49.8. We have 1,400 that are less than great 49.8. I'm just going to delete 49.8 less 51, and we're also going to be 39 less 48, and we have 262 are between 52.5 and 51. And excuse me. Oof, that's probably very grating. 1,600 are between 48.2 and 52. So let's go ahead and let's solve this problem. And I'm just going to solve it in mathematics, obviously. You can try to solve it in R as well. So our observed, go ahead. Let's do our observed right here. So observed numbers, 950, 1,400, 39, 262, and 1,600. Our expected is going to be, let's go ahead and we're going to integrate. So our expected values, so we have 50 and then a standard deviation of 1. So we find 950 greater than 49.8, so expected 1. We have our z function, and actually we have to, let's make sure that we shift enter our z function. So our x is 49.8, and then our mean is what? 50 and 1? Yeah. 50 and 1. So we're saying we should expect that many, and then how many, what's our total? 1,700. So this should be the number that we expect that is greater than 49.8. And there we go. Now we can do the same thing for expected 2. So we're going now, actually I'm just going to copy here. Expect 2. Be careful, make sure that we do it. So we should be going from minus infinity to z function of less than 51. So we'll delete this infinity. Let's just look at this numerically. That's expected 2. All right, expected 3. Let's do less than 48. 48. And then finally, or not finally, but expected 4. Between 51, so should this do actually 52.5, and then we'll do 51 here. There we go, and then finally expected 5, and that's going to be 48.2 and 52. Great. So we have our observed, we have our expected, and so now what we're going to do is we're going to do observed minus expected. So now we're going to do our hypothesis testing. So again, we're asking the question basically, is it normally distributed from at a significance level of this? So we calculated our chi-squared value. So we have that experimental value. our chi-squared theoretical, remember it's never going to be an alpha divided by 2, so it's just going to be, our alpha is going to be 0.1, and remember our nu is going to be equal to what? Equals k, which is the number of variables, which is 1, 2, 3, 4, 5. 5 minus 1 minus r, which is our number of variables, which in this instance, normally distributed. So we're looking at fitting a mu and fitting a sigma, 2 variables. So our nu is going to be 2. And we can look at that. Let's go ahead. Let's get out of here for a second. Let's move us a little bit. We need to open, actually. Let's open our chi-squared. Should be lecture 6. Where's lecture 6? Let's see our chi-squared table. So here we go. Chi-squared, 0.1 of basically 2, so it's 4.605. 4.605. And we are looking at basically that right-tailed test again. Basically, we're looking at those values. So let's go ahead. Are we in the reject or do not reject regime? Let's go ahead and look at. It's always going to be a right-tailed test. So are we beyond that value? Let's go ahead. Where are we at? Where's our? Oh, excuse me. So our chi-squared is 1.9. So we are in the do not reject regime. If we look over here. So right-tailed test, we are do not reject. Fantastic. So let's go ahead. So we can do now something similar for this next problem. So let's go ahead. Do a goodness of fit chi-squared test again. Recently, etc. About 800 chocolate, pick one box and pandem. So I took 800 samples now. So instead of the 1700, we're going to do 800. But my observed list now looks like, so we did 360. Ooh, actually, this is an interesting one. So let's see. Recent Halloween Godiva, so it should have 12 peanut butter, 5 fruit filling, 8 with caramel, 2 with coconut. So I did samples. So we have basically our outcomes could be PB, fruit, caramel, coconut. So that's the probabilities that we have. So we're going to have an expected, and our expected versus our observed. So let's look at our observed. Our observed was 360, 140, 250, and 50. And our expected should just be basically claim. So it should be, so our tote Godiva is going to be equal to a total of 12, 5, 8, 2. So my PB equals 12 divided by tote Godiva. My caramel, or actually my fruit equals 5 divided by tote Godiva. My caramel equals 8 divided by tote Godiva. Actually, we call it caramel. And then my coconut equals 2 divided by tote Godiva. So my expected values should be equal to, and I'm going to keep this in the same order, PB times 800, because that's the number of samples basically that I did. Fruit times 800, carm times 800, and coconut times 800. My observed, that's my expected. My observed are those values that we wrote down here, which are equal to 360, 140, 250, 50. Observed, expected, we can just run our value again here, and it should change. So that's our chi-squared experimental, 2.65. This number of outcomes, 1, 2, 3, 4, we're not asking if they're normally distributed. So my chi-squared theoretical is going to be 0.01, comma, k, which is 4 minus 1, which is going to be 3. And that's going to be equal to, let's get this out of the way. Move a little bit. Just a little bit. So chi-squared of 0.03. Let's look at those. 0.01 and 3 is going to be equal to 11.345. So we are do not reject again. Got it. All right. The next problem is an air propagation. And so is problem 5. And let's see. And so is problem 7. So what I want to do right now, while we're still thinking about kind of looking at if our things are normally distributed or not, we can go ahead and I want to actually calculate this next problem. So let's look at basically looking at vulcanization. Degree of cross-linking, 0 to 1. So we should have a mean of this, standard deviation of 0.25. Text box 500 samples. So we find observed, expected, and then our values. So 70 between 0.1 to 0.3, 70, 140 between 0.2 and 0.4, and then 240 between 0.3 and 0.6, and then 70 between 0.7 to 0.9, and then finally 420 samples between 0.3 to 0.8. So let's go ahead and put those down again. So I'm going to put my observed. My observed now is going to be, again, 70, 140, 240, I think 70, and 420. Let me make sure that is indeed true. Let's just double check that. We should, because just do that right here. Just want to grab this. Just move some things around here. Let's see if the numbers are correct. 70, 140, 240, 70, and 420. Good. So let's go ahead, and then we're also told, so let's go ahead and do the first one. So actually we have 2 z values for expected 1. Our total should be 800, or actually 500 samples, and we're testing that one between 0.1, and then the mean should be 0.5 with a standard deviation of 0.2. So let's go ahead and copy this over to here, and it's also 0.1 and 0.3. So that's our expected 1. Our expected 2 will be very similar, except now 0.1, 0.3, 0.2, and 0.4. So all we have to just do now is change this. Good. Expected 3 will be very similar. Expected 3 will be between 0.2, or actually we did 0.4, 0.3, 0.6. And again, you can do this by looking at the charts as well. Whichever way you can do it, efficiently as well. 0.7, 0.9. And then finally, 0.3, 0.8. Got it. So now we have our experimental, whoops. We need to, yes. Experimental 1, 2, 3, 4, 5. Let's shift enter that. Make sure that we're good here. 1, 2, 3, 4, 5. There we go. So our chi-squared. Sorry about that. Our recording suddenly quit on us. But anyways, our chi-squared experimental then, chi-squared experimental is going to be 8.5 something. You can look back there. Fantastic. So we also know that we have 1, 2, 3, 4, 5 variables, but k minus 1 minus r, because we're looking, is it normally distributed? So that's going to be minus 2. So that's going to leave us with 2. So our chi-squared, which 95% confidence interval, 0.05, 2 is going to be equal to, let's look at our 0.05. Let's go to 2. So 5.991. So is this normally distributed? Do not reject. There we go. So we got this one as well. Let's go for the last one that is in this kind of, are we normally distributed or not? So bio company forces this. We see the impact of the law. They claim the impact for is normally distributed with a mean of this, standard deviation of this, 700 samples. So again, unobserved, unexpected, and then we can see the value. So I find 670 between 50.1 to 75. I see 690. That should be less than 75 kilonewtons. I see 660 greater than 53.5. 660? Yeah, 660. And then I have 67 between 50.1 to 53.5. And then finally, we have 51 samples between, or less than 53.5. And then finally, actually, 650 between 53.5 and 75. So let's go ahead. We're experts at this point. So I'm going to go ahead and first write down our observed. So our observed is going to be, so we're going to have 670, 690, 660, 67, 51, and then 650. So we've got that there. Our observed is going to be 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, and then let's do an expected 6. Let's go down here because I want to go through these expected 1, expected 2, expected 3, 5. Let's go through here. So I'm going to do an expected 1 equals. So first, it's going to be between two values. So actually, I'm going to steal this. And then our samples are 700 samples. So we need to change this to 700. So expected 1. So I'm going to do, but my mean, actually we're looking at between 50.1. Our mean is 60. And then our standard deviation is 5. 50.1 and 75. So let's go ahead and do 75. So that's our expected 1. You can copy and paste this. Expected 2, less than 75. So actually, I'm going to keep this. So I'm going to go minus infinity to this. Let's look at this numerically. Good. And then we're going to have expected 3, which is greater than 53. So let's go back. Actually, I'm going to just delete this. 53.5? Yeah, 53.5. And then I'm going to finish it off with an infinity. Almost there, people. Expected 4. We're going to have between 50.1 and 53.5. So I'm just going to copy this. 50.1. Good. And then we're almost there. expected 5 is going to be less than 53.5. So we're actually going to go minus infinity to 53.5. And then between 53.5 and, I'm actually going to copy it over here. I'm going to call this expected 6. Because we're going to go 53.5 and 75. Alrighty, so let's go up. Let's shift enter this. Now we're going to go find our chi-squared experimental. So our chi-squared experimental is 11.2. So our chi-squared, we are looking at this. It doesn't give us a value, so 0.05. We have 1, 2, 3, 4, 5, 6. So 6 minus 1 minus 2, so that's 3. Because again, we're looking at normally distributed. And then finally, 0.05, 3, 7.815. Where are we? Reject. There we go. Now, the rest of these problems are all about propagation of air. So we need to figure out, are we dealing with bias air, precision air, or both? So it's time to do some reading here. So let's start to go ahead and read through the statement. Measuring ligands, Helmholtz coil, we're given this fundamental equation here, where this is a distance that's measured, translational displacement, frequency, time of actuation, and radius. The rolling parameter, dimensionless number from 0 to 1. Experimental screen where there's, so let's go ahead and do that rolling parameter. 8 as a function of delta x, omega, tau, and my radius. So, all right, run my experiment. This conversion is just 1-to-1. So for micrometers to pixels, I use a custom mathematical resolve up to 0.1 pixels. So the pixel is going to affect this and this. So there's going to be a bias error or an uncertainty in delta x. It's going to be equal to 0.1 times 10 to the minus 6 meters. Same thing, uncertainty in the radius, which is going to be 0.1 times 10 to the minus 6 meters. DAX is resolution of 1 nanosecond, so uncertainty in a tau, that's going to be 1 times 10 to the minus 9 seconds. 10% of a given frequency. Let's see here. So, and then my uncertainty in my omega is going to be equal to, let's see. Nominal diameter should be this, blah, blah, blah. Nominal frequency is 1 hertz, so 0.1 hertz for that uncertainty. So I have bias error in all these variables. Measured 17 times, found a mean of this. So there is going to be some precision error in the displacement delta x, and that's just going to be equal to 17 times. So it's going to be equal to my t alpha over 2 nu times my standard deviation, which is given here in delta x over square root of n, which is 17. And then we're going to find this value here. Excellent. Nominal diameter should be this. I measure the actuation time, so the same thing, precision error in tau, which will be again, t alpha over 2 nu. But we know this value should be 1.96, but we'll get to that. Standard deviation of tau over square root of n. There we go. So calculate the total uncertainty. So let's go ahead and let's get at it. So I'm going to actually write out all these values, and we're going to do square root of the bias, all that good stuff. So actually, I'm going to quit my kernel here because we've been defining lots of things. So let's go over here. So I'm going to define my expression. So RP is going to be equal to del x divided by 2 times pi times r times omega times tau. So there's going to be some uncertainty in del x, which is going to be equal to 0.1 times 10 to the minus 6. There's going to be some uncertainty in r, which is going to be equal to 0.1 times 10 to the times 10 to the minus 6, where there's going to be some uncertainty in tau, which is going to be equal to 1 times 10 to the minus 9. And there's going to be uncertainty in W, which is going to be equal to 0.1 hertz. So we're going to shift enter all that. So my total bias in RP is going to be equal to square root of, and I'm going to do now d del x is going to be equal to derivative of RP with respect to del x. My d r is going to be equal to derivative of RP with respect to r. My derivative of my, actually we can keep this, my derivative of my, derivative of omega is going to be equal to derivative of RP with respect to omega. And then my derivative d of tau is going to be equal to derivative of RP with respect to tau. So my square root down here, isn't this fun? Square root of, let's go ahead and do uncertainty in del x times d del x squared plus, so we're going to copy this and just change, because I need to do it for omega, tau, and r. So u dr, or u uncertainty in r, dr, uncertainty in omega, not u compress. Where's the uncertainty? UW, U del x, UR, UW, d omega, and then U tau, d tau. And you see we have like these values here. We need to substitute in what the nominal values are. So a mean displacement, which is going to be, so del x goes to 100 times 10 to the minus 6, are the nominal, let's see. So tau goes to 5 seconds. Our frequency, omega, goes to 1, and then our radius should be a diameter of 9, so our radius goes to 4.5. So that's our bias there. So now we have, though, precision, and because, so we have the number of del x equals 17, the s del x is going to be equal to 2 times 10 to the minus 6, and then x del x equals 100 times 10 to the minus 6, and then finally we should have the same thing for n tau equals 98, x tau equals 5, and then s tau equals 1 times 10 to the minus 6. Yeah, there we go. So now we have precision in del x, which is going to be equal to, what is our alpha over 2? We're working at a 1% significance level, so we need to have 0.005. So let's go back over here. T is 0.005, should be 16, 2.921. So let's go over here, 2.921 times my s del x divided by square root of n del x. But importantly, these are in units of what? Basically micrometer. So we need to divide by x del x to turn it into a percentage, because, and actually that's going to change our answer here. So we need to divide this whole thing divided by RP. So we need to normalize it by basically the functions that we were working with here. So divide by RP, divide by our function, and divide by our function as well in here. So that's our percent here. That's our percent there. I know because we're doing large sample size that it should be 1.96 S tau N tau, and then divide out by X tau to make it dimensionless, P tau. So now I can do the total uncertainty equals square root of what? Percentages. BRP squared plus P del X squared plus P tau squared. And we can see clearly the large contributor is that bias error. Some in del X, but not significant. And then there we go. Fantastic. So that's the first one done. Very long, very arduous. But again, if you follow those steps, you're going to be absolutely just fine. So let's go ahead and let's move through and go to the next one. So let's look at our next problem. So we have another fundamental equation right here. We have a constant. We have a radius, number of turns, current. X is the distance from the coil. We're looking to measure basically at this half distance, but this doesn't matter. So to achieve magnetic field strength, blah, let's see. Result is just this. Actually, yeah, we actually want to keep this. So now it's just a function of the constant N, I, and R. So what are some uncertainties we can have? I need 10 millitesla strength, no more than a millitesla uncertainty, 500 turns of wire. So there's uncertainty in the number of turns, plus or minus 10. So we have some uncertainty in N, and that's going to be equal to 10. Constant with this value times 10 to the minus 6. Measure the current. So no uncertainty in R naught. Handheld ammeter, some uncertainty in the current of 1 times 10 to the minus 3 amps. And standard deviation. We're using a ruler, so I'm going to say that there's going to be some uncertainty in R as well. And that uncertainty is going to be, I'm going to assume that I have a millimeter tick mark. 1 times 10 to the minus 3 meters. So I have uncertainty in all of these. I'm also going to have some precision error in current, which is going to be large. So it's going to be 1.96 because I'm doing 95% confidence interval times standard deviation of current over square root of number of measurements of the current. And I believe that is it. So let's get to it. I'm going to go ahead and quit my full kernel. Quit everything here. My fundamental equation is going to be B helm equals 8 times mu naught times big N times big I. You'll see why I'm doing that in just a second. 5 times square root of 5 times R. And then here we go. So we're going to say also that dn is going to be equal to derivative of B helm with respect to N. We're going to also say that di is going to be equal to derivative times, or derivative of B helm big I, and this should be actually big N. And then finally, dr is going to be d B helm R. We're also going to state, what else do we have? That mu naught is a constant, so I'm just going to type that in here. Usually I don't do that. I just kind of temporarily assign, but I'm going to do that because there's no uncertainty in this one. We also have number of I measurements is equal to 35. Xi is going to be equal to 5 amps. Si is going to be equal to 0.1. Good. I'm going to calculate precision error right now. So PI is going to be equal to 1.96 times SI divided by square root of NI. And I'm going to divide all of this divided by XI because we need to make sure that we're unitless in our precision error because we have a large bias error. So the bias in Helm is going to be equal to square root of, and actually let's define our uncertainties, which we already wrote over here. So U of n is equal to 10, U of I equals 1 times 10 to the minus 3, and U of R equals 1 times 10 to the minus 3 as well. Those are our values, not L. Good. So our square root is going to be, for example, dn times derivative n times un divided by b Helm squared. Again, we want to make that unitless, so let's add that. So we're going to do this 3 more times. Good. So dn di times ui, and then finally r ur, and then that's going to be my b Helm. And I'm going to do slash dot. We have to basically put in those nominal values now at this point. Slash dot. Big I goes to xi, which we've already defined. We said, what's our nominal value of current? We've already said that. 500 turns. So big N goes to 500. And then big R, actually just do R. R goes to what? I do have some uncertainty in the radius. 14 times. Oh, wait, I gotta get that. So I have some uncertainty. So XR equals 7.5 times 10 to the minus 2. We also have SR is going to be equal to 0.1 times 10 to the minus 3. And then finally, NR is going to be equal to 14. So we're going to have to, unfortunately, I'm going to do XR right here. Not unfortunately, but this is the reality. So I'm going to have to go ahead and we're going to have to do PR equals T to the 1 half. So we need to do T of 0.2513. 0.2513. So it's 2.16. So I'm going to have to do, for my precision error, 2.16 times SR divided by square root of NR. And then I'm going to do this whole thing divided by XR. And there we go. So percentages. So now total uncertainty in Helm is just going to be equal to square root of parentheses, actually not even parentheses, B Helm squared plus PI squared plus PR squared. And there we go. So you're looking at about a 30% uncertainty. If we look at some of the, obviously the biggest chunk, actually not 30%, about 3%. Biggest chunk is going to be from our bias. All right. And one last one. So now we're looking at pressure, basically ideal gas law measurements. Let's see, measure with the ruler, so centimeter tick marks, using this function. Measure below are my measurements. We don't need to deal with this one here. That's a little error. So we're looking for some uncertainty and pressure, and critically here, we're going to be using something a little bit more uncommon, which is going to be that 99% confidence interval. So let's go ahead and rewrite our function. So P is a function of N, R, T, and V. And let's go ahead and read this. Gas constant. Let's see here. Number of moles should nominally be 10. So there's some uncertainty in the number of moles, which is going to be equal to 0.1. let's see, thermometer, so some uncertainty in temperature, which is going to be interval degree markings, temperatures in 1K, good, so 1K. What else do we got here? Temperature, what else did we measure? Does it tell us the tool that we used? Okay, so here we go, tick marks. So for the volume, ooh, this is another trickier part. So this is a cylindrical pressure vessel, so our volume is going to be equal to pi our radius squared, or pi times diameter over 2 squared times the length. And there's uncertainty in the diameter, which is going to be, so instead of volume, we're going to write it as the radius and the length, or the diameter, excuse me. Uh-oh. So R and L. So there's going to be uncertainty in diameter, which is centimeter tick mark, so 1 times 10 minus 2 meters, which is going to be equal to uncertainty in the length. So that is going to be, there's no uncertainty in R. So we have bias here, 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 and here. We also are going to have, obviously, precision here, here, and here as well. So let's go ahead and let's start with probably the more annoying part of this problem. And actually, let's go ahead, and what we're going to do is we're going to do quit the kernel, local. So I'm going to say I gas is equal to, actually P gas. P gas is equal to N times R. I'm just going to put, instead of R, times 8.314 times T. I'm just going to call big T. Big T divided by pi times diameter divided by 2 squared times L. And I'm going to also make right now, I'm going to make this a D list, which is going to be 0.7, 0.8, 0.76, 0.81, 0.76, 0.6, 0.7. I'm going to make a, I'm going to also make a D list, L list, 1.3, 1.32, 1.28, 1.21, 1.37, 1.4, 1.25, and then we're going to do T list, which is going to be equal to 300, 299, 305, 300, 307, 295, 301. I'm going to look at the length of all my lists just to make sure. D list, L list, 7, and then T list. Good. So now I'm actually going to do the precision error first. So all of these will have basically that T value. We're going to use a 99% confidence interval. So it's going to be 0.005. And then we have 7 measurements. So it's going to be 6, 3.707. So my precision error in D will be equal to 3.707. Let me just make sure that was indeed correct. 3.707, yes it is, times, and I'm going to do standard deviation. Standard deviation of my D list divided by 7, even though I don't, divided by square root of 7, excuse me. And then this whole thing, we're going to divide it by the mean of our D list. So that's going to be, again, that precision error in D in percentages. We're just going to copy this. So PD, PL. So we're going to do L list. We're going to do L list here. And then finally, we're going to do T, PT, T list, T list. And there we go. So those are our uncertainties. Now we're going to do P gas. We're going to do DN is equal to derivative of P gas with respect to N. D big T, actually I'm just going to do dt, equals derivative of P gas with respect to big T. And then finally dd, actually not finally, derivative of P gas with respect to D, and dl equals derivative of P gas with respect to L. All right, so now we can do the bias in P gas, which is going to be equal to square root of parentheses. We also need to do the uncertainties. So uncertainty in N equals 0.1, uncertainty in T equals 1, uncertainty in D equals 1 times 10 to the minus 2, and uncertainty in L equals uncertainty in D. So let's do uncertainty in D times dd divided by P gas squared. You're all experts at this point. Putting it in percentages, because again, we have to deal with precision error. 1, 2, 3 more. So uncertainty in L, dl, uncertainty in N, dn, and uncertainty in T, dt. And I'm going to get rid of that. We're going to have to, slash dot N, I think the nominal value they said was 10. Yeah. N is 10. D goes to mean of D. D list. Let's go ahead and pull this out a little bit. D goes to mean of D list. L goes to mean of L list. L goes to mean of L list. And then finally, big T goes to mean of T list. So now we just add all those up. So now we do square root of PL squared plus PD squared plus PT squared plus bias P gas squared. And we get a value of around 16%. Interestingly, it's the precision error in D that dominates. So that's it. The problem set is finally mercifully over. So congratulations. See you in the next one. Thanks. Bye.